Welcome everyone. The speaker today is Vatsal Jha. He's coming to us all the way from Purdue. He's a PhD student advised by Elena Grigorescu and Eric Samperton. And he tells us about codes and the hardness of computing the distance of codes.
So, thank you for having me here. So, I will be talking about basically what are graph states and the problem of computing the graph states and why that problem is NP-hard. And along the way, we will be seeing some results which are interesting in their own right. Okay, so let me be a bit pedantic and start by talking what are binary linear error correcting codes. So a binary linear error correcting code C with parameters NKD simply means a subspace of the n-dimensional vector space over F2 with dimension K and having distance equal to D. The having distance of a vector, of a binary vector, is just the number of non-zero positions in that vector. Right. So now a compact way of representing a binary code or a binary linear code is via matrices, via the generator matrix or the parity check matrix. And your code is simply either a row space of G of the generator matrix, or it's a null space of the parity check matrix or the kernel of H. Associated to every code, you also have a dual code or the Euclidean dual code, which I denote by C per. And it's basically the set of all vectors which are orthogonal to every code rule. And the rule of the parity check matrix and the generator matrix for the dual simply switch over. So your C dual is nothing but the row space of H and the kernel of G, on contrary to what you had for the classical code C. Oh. Yeah. So now the distance of a code essentially characterizes its error correcting capability. Meaning that if your distance is large, then it can correct large number of errors. And it's natural to ask whether I can compute this distance efficiently or not. So in other words, given this decision problem, which I denote by minimum dist problem, where the input is a parity check matrix, a full rank parity check matrix, and a positive integer t, it outputs yes if the distance of the code is at most t, and it outputs no if it's not the case. The answer for whether you can compute it in polynomial time or not was given by Vardy back in 1997, saying in which he showed that this problem of MDP is actually NP-hard. Now, recently, like switching gears, recently Kapshikar and Kundu in 2023 solved a similar problem, but for quantum codes. What they showed was computing the distance. So it's a very informal way I have stated it, because I will be defining what is the notion of distance of quantum codes, or what are quantum codes for that matter. That computing the distance of quantum codes is NP-hard. So in this talk, what we will be looking at is, like, the outline of this talk will be what I will be focusing on, what are graph states, then what is the hard, like I will be talking about the hardness result of computing the distance of graph states. And at the end, as promised, I will also show that computing the minimum distance problem for 8 half codes. So if your universe is only containing of 8 half codes, that problem is NP-hard as well. Okay.
Good question. So these hardness results are under deterministic polynomial time reductions?
Yeah, deterministic polynomial.
There was my memory is being very foggy. There was this result of Doomer, Sudan. What was how was that related to what?
Yeah, so that was for the approximation.
Oh, I see. Oh, this is exactly determining.
Yeah.
Okay.
And recently, even for the approximation, Guruswamy et al. Showed that you can actually convert that RUR reduction to a determinant.
Okay.
And why are rate half codes interesting? Why not rate one third, rate one fourth, why not?
Like for any constant rate codes, like can you show that is it NP hard or not? So like the reduction that they followed was they showed it for asymptotically large, like approximately one. In the reduction, it was approximately one. So it was
The
not
rate was
known.
approximately one.
Yeah. Okay, so now let me first talk about what are quantum codes. So
Wait, sorry, just to confirm. So you're saying that if I show that rate half MDP is NPR, I also show rate one fourth MDP is NPR.
yes, by padding more zeros. Yeah, by padding number of appropriate number of zeros. Yeah. So now, yeah. So for quantum codes, a quantum code Q is essentially a quantum code Q of length n is essentially a linear subspace of the n-fold tensor product of C2. So it basically means that you look at the Hilbert space of dimension 2 raised to n, the complex Hilbert space of dimension 2 raised to n, and you look at a subspace of that, and that is your quantum code. So that's the definition. And the problem of finding good quantum codes. So okay, so it should be not this way, just the other way. Yeah. So the problem of finding good quantum codes can be like a sufficient condition for that is problem of finding good subspaces. So it can be like if you are able to find good subspaces, like I will be defining what good is, then you can find good quantum codes. Right. So in particular, usually, like in literature, the most popular studied quantum codes is the family of stabilizer codes. And the reason is that, as mentioned above, you want to find good subspaces. So why not like one way to obtain those good subspaces is obtaining good eigenspaces of operators. And since operators are a
We haven't
bit
yet defined what is the good subspace, right?
yeah.
Okay.
And the idea is to obtain a good, like, in order to obtain good eigenspaces, you can essentially focus on operators or good operators. So this stabilizer formalism or this idea of stabilizer codes was introduced in two works, one by Gottsman independently in 1996, and the other one was a bunch of people with Cadabank, Shaw, Sloan, etc. In the same year. And as mentioned, the idea is to focus on eigenspaces of operators that act on this Hilbert space. So for n equals to 1 case, your operators that you want to focus on, or the eigenspaces that you want to focus on, are essentially the eigenspaces of these operators, like which are mentioned on the board. So this is the usual identity operator. Second one is your quantum bit flip gate, because you can see that if you give a 1 0 to it, it flips and gives an output of 0 1. So that's why it is called the bit flip. This is the Z gate, which basically is known as the phase flip. And the last one, the Y gate, is a combination of the bit flip and the phase flip. And the one reason why this set of operators is considered to be interesting is because they form a basis of your linear space of operators on acting on a single, like all your 2 cross 2 matrices can be written as a linear combination of these. And also on top of it, they are symmetric, so they are diagonalizable. So they have eigenspaces. Now for general n, what you focus on the tensor product of these things. So alpha, each of these alpha i's is coming from this set, and for general n, you focus on operators of this kind, and you talk about the eigenspaces of them. So now, like right now, we were focusing on a eigenspace of single operator. Why not consider the joint eigenspace? Like consider a bunch of operators and look at the joint eigenspace. And that's a folklore that if you want to have a joint eigenspace, then the set of operators that you considered, they have to commute with one. Right. And like by set of operators, you can also consider the group that is generated by. Right. And but still, I mean, even this picture of considering operators as such is not that much, like it does not give you that much advantage or that much power.
So if GI is termed, what can we say about the current eigenspace?
So a joint eigenspace exists.
I see.
So if they did not commute, you couldn't comment that okay, they had a joint eigenspace.
There's even one. There's even one vector which is a whatever an eigenvector of all of them.
Yeah.
We can't say it. So that.
Yes. So it's like if they do not commute. So in particular for these kind of operators, what you can see is either they will commute or they will anti-commute. That's the nature of these operators. So if they do not commute, they will anti-commute. Right? So if they are anti-commuting, then the only eigenvector that satisfies that is the all-zero vector.
So here, suppose that DI is commute, then the statement is that there is a set of linearly independent vectors, how many of them that happen to be the eigenvectors of each of the GI.
Yes, so you can diagonalize them in that basis, in that particular basis.
And this, sorry, no, go ahead. This G1 to GR is one of these operators, or it could be anything.
It is one of these operators.
I see. So this result is not a general thing. It's just
but since we are focusing, so since these happen to be a basis.
No, that is a general.
That's a general.
That's the state of the
Yeah, this is a general.
Pauli sir, this is, but that's a very general.
okay. So even for a general set of things, even if there is one common eigenvector, it has to mean that they all commute.
It's not
True. That is not.
If they have the entire eigenspace has to be the same, then they have to compute. Or they are simultaneously diagonalizable, basically. And they will compute.
And that's one thing I'm a little confused about. So here, are we saying that there is an eigenbasis sort of a thing, or are we just saying that there is a common eigenvector?
No, eigenbasis. So you can diagonalize. There's an eigenbasis. You can diagonalize all these operators using that eigenbasis.
Okay, but isn't the following true that if I have a bunch of operators that I know commute with each other, typically the best that I can say is that they are simultaneously triangularizable. Right? I thought that simultaneous diagonalization feels too strong to be.
That might be true, but these are, we will eventually only be considering these matrices. That is poly matrices. So those.
Or maybe
for those, what you say is true in general. You won't be considering arbitrary unitary matrices, only unitary matrices that appear as tensors of.
Yeah. So yeah. So a way to go from meet. So since we like to work in linear spaces over finite fields, Catabank in 1996 provided a way. Catabank, I thought I should be more specific. Provided a way of converting each of these operators as the binary vector. So you can visualize that each of these GIs, you can actually visualize them as a pair of n-bit vectors, AI, comma BI. And this commutation relation that you have is in fact a orthogonality condition, but with a different inner product, not your usual Euclidean inner product. So if I have gi comma g sub I comma g sub j equal to g sub j comma g sub I, and if their corresponding vectors were ai comma bi and a sub g comma b sub g, then the condition is this commutation is exactly equal to this inner product being zero.
Sorry, what is the hypothesis of this here? Like, say if something is true, then these things are true.
No, so it's like you can actually like okay. So if you're taking GIs from this set of vectors, then you can write it like this.
It's an isomorphism from these matrices to F2m cross F2m. It's an isomorphism in some sense, certain thing to this one, so that two matrices commute if and only if the corresponding symplectic inner product is zero.
Yeah. 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 And now extending on that, if I want that a set of or a group of G1 to GR should commute, that is equivalent to saying that the subspace, or like I should be writing it as the subspace AI comma BI is self-orthogonal with respect to symplectic inner.
No. It means it's weakly self. It's contained in the dual. It's not equal to the dual.
So, by the definition, by this term self-orthogonal, I mean it's contained.
Okay.
Like I would be using self-dual for that.
So the image of this
Yes.
thing is contained in its dual
Yes.
under the inner product.
Yes. So this is contained in its.
Yeah.
Yeah. And so, like you, one can associate a matrix to this. Like you can stack all these generators that you had into a matrix format of A and B, where this is of dimension. So if you had R many generators, then you will be having R cross a matrix of dimension R cross 2n, such that
This is a matrix over F2?
Yes.
The matrix, okay.
such that A times B transpose plus B times A transpose should be the. And this condition is essentially this self-orthogonality condition. Okay. So now, in this picture of stabilizer codes, one can define the notion of a distance in a similar fashion as how we define it for classical codes. So for classical codes, you have a parity check matrix and you look at the least weight vector such that h of x equals to 0. Over here, the role of parity check matrix is taken over by this matrix, and the distance over here is essentially a vector of least symplectic weight. I will be defining what symplectic weight is of least symplectic weight such that this is equals to 0. So, should I be writing it this way? Yes, so B. So, yeah.
So we should think of this AB as a parity check.
Yes, that's one way of thinking.
Sort of, but not exactly.
Yeah, I mean, sort of. I mean, over here, this inner product, you cannot consider it as a Euclidean inner product in the first place. You have to consider the symplectic one. But
This matrix vector multiplication that you're doing.
yeah, but you can actually flip it. Like a symplectic inner product of AB and CD is a Euclidean inner product of AB and D, comma C. Yeah. So I can, whatever vector I have, if it was x comma z, I can just flip the values, and that is still in the same thing. And yeah, so now I have to define what do I mean by symplectic weight, or
Well, you haven't, you told us how to check how to code is specified. That is this either in the set of generators or after going to this matrix, but you haven't yet said what the code is, no?
yes,
Yeah.
yes, and yeah. So yeah, I think that should be like I should mention that before. So
In that language, it is the eigenspace corresponding to eigenvalue 1 is the
yes, the joint. Yes,
the subspace corresponding to the eigenvalue 1 is going to be the code in that language. Oh,
yeah.
Okay.
Yeah. So yeah, so the stabilizer code, if I want to say the stabilizer code corresponding to a set of generators is essentially the joint plus one eigenstate. So it's the set of all vectors psi in this n-fold tensor product such that it's the plus one eigenstate for all of them.
Right. So I should be thinking of this as saying G is going to be some subset of those tensor products.
Yes, yes.
Okay. Now, once you choose a certain subset of tensor product, the code that this subset of tensor products define are these set of states.
Yeah, and since I want this to happen, I want them to commute.
Yeah. Okay.
Yeah. And that commutation relation, if I want to represent it in terms of binary vectors, I can have that condition or this condition for that matter.
So, we want the GIGJs to only commute, not anti-commute.
Yeah.
Only complete because then it doesn't make sense.
Yeah. Oh, yeah, sure. Yes.
Okay. And yeah, and the okay, so now you want the symplectic weight of a vector is just the weight of the bitwise or the Hamming weight of the bitwise or of these quantities. Yeah, so the intuition I would
What is bitwise what?
yeah, this is a bitwise or A and B. So if A and B are two n bit vectors, the symplectic weight is essentially the Hamming weight of this vector. Yeah, and the idea is that the reason why it is defined in such a manner is that if even one of these indices I, if even one of the indices I corresponding to either A or B is 1, then you can say that the ith qubit of your system was affected. Alright.
Okay. This is just the definition of weight.
Okay. Is it fine if I erase this?
So I should be thinking of A as basically saying these are the bit flips that happened, and B's are saying that these are the phase flips that happened.
Yeah,
And you're basically saying how many qubits did I affect?
exactly.
I see.
And now we will be focusing on a special class of stabilizer code. So this was the entire, you can say, formalism for stabilizer codes, like what is the distance and what is the how you define them. You can, like, we will be focusing on special class of them, which are known as the graph state distance.
Sorry, Vatsal, how was it apparent from what we've seen till now, what you said?
So I was just trying to get a sense of how should I interpret this thing. So maybe this A comma B, when we are trying to minimize the whatever norm such that something happens, maybe I should think of this as the error vector that I have in the system. So maybe A refers to saying that there is something that happened which did some bit flips on some set of coordinates. And B is saying that on these or whatever on these whatever states, qubits or something. There are some phase flips that happen. And I was just trying to interpret what weight of A or B. Yeah, saying that okay, there aren't too many states that were affected, and then I want to say that something can't become zero.
Oh.
Yeah.
Okay. Yeah. So now, so now we will be focusing on a special kind of stabilizer codes, which are defined using graphs. So, okay, so for a undirected, unweighted graph, so G is an script G is an undirected and unweighted graph. Okay. Okay, define. Do you define?
The subspace in the language of generators.
Yeah.
What is the code in the language of these matrices A, B? You have, or it's not. It's that.
It's not. I mean, it does not get translated. Okay. Only the distance gets translated.
Only okay.
And the generators get translated, but the code itself,
Okay.
because it's the +1 eigenspace, so that does not get translated.
Okay.
Yeah. Yeah. So you have an undirected, unweighted graph, and just for like on n vertices, so this is identity on n cross n. So one can check that this does satisfy the stabilizer condition, which is of I times AG transpose plus AG times I equals to 0, owing to the fact that adjacency matrix is symmetric and we are working over F.
Sort of slight type mismatch. So in this case, R is equal to N.
Yes.
Oh, okay. Okay.
Yeah.
Okay.
And now the question is, so this is
sorry, this is over F2.
okay. Yeah. So now, yeah. So
Isn't that issue? Isn't the number of logical bits, the space of the logical bits n minus r?
yes. So that's why it's called the graph state. So it is encoding just a single qubit.
So there is no. It's not a. It's just a single
qubit. Yeah. But you can. There's a way of going from single qubit to multiple qubits using this graph state, but it's a different direction altogether. That's known as code word stabilized formalism.
So then I'm good at work. There's only one code word in this space.
Yes.
What is distance then?
The distance is this definition.
Okay.
Yeah. So it for even for zero logical qubits, you can actually define the distance in this following manner.
So it will be the minimum symplectic weight vector,
Yeah.
a non-zero vector that.
Yeah. That satisfies this set of equalities. Okay. So, okay, so now we can talk about the graph state distance for this, and that is going to be essentially, let me just write it over here. The decision problem is going this, then graph this, where the input is a graph or the adjacency matrix of a graph. And an individual D. And the output is yes. If the distance, this is the graph state distance, is at most T, no otherwise. And the claim is, so let me write it as claim 1, that this min graph dist is NP Hardness. That's the claim that we want to be. So, in other words, what we want is we want to reduce. So, the reduction is from the minimum distance problem to this min graph distance. And so what we want is we want to convert every instance over here, H comma T, to an instance S and T comma T. So before that, before proving this, let me first look at a promise version of this problem.
How do these transmission codes compare to classical codes? Like, is there a way of, I mean, there's a reduction here. So, I guess in some way you do this translation, but is there something sort of more general that one can say about?
Well, that will
interpret for every classical family of course with blah 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 parameters
as a graph.
There's a natural interpretation in this.
I mean, there's not. I mean, this reduction uses that. Like we use that. So,
what about if you are looking at stabilizer codes in general?
So in stabilizer codes, in general, you do not need that picture. So you just need like you can generalize it like the way of lifting classical codes to stabilizer codes was given by CSS construction, where you can take a bunch of a pair of classical codes which satisfy certain properties, and that you can lift. But in general, you cannot lift every classical code to a stabilizer. So only for particular subclass of stabilizer codes you can do.
And what does one cannot mean?
Like by cannot I mean there's no well-defined formalism or well-defined way of doing.
As far as you know.
Yeah.
In a sense, there's more you're requiring of the code. The code, classical code only withstand bit flips. These are to withstand phase flips. The objects you plan and
Are strong.
Stronger, and it's also classical codes. You are giving only bit length strings. Here you are going to give these vectors, and these are not the same as. For example, an encoding of just the logical 0 bit can be something which cannot be written in the classical world at all. It can be a vector in this world, which is, it can be 0 plus 1 by root 2. I can't, 0, 0 plus 1, 1 by square root 2. I can't write it in the classical world.
Okay, so the claim 1 prime is essentially saying that, okay, what if I was given the promise that this z vector is 0? So I can write this system of equations equivalently as a sub g x equals to z. So now if I'm given the promise that this is all 0, this is the all 0 vector, what can I say about the hardness of this promise version? Is it in P or is it still hard? So the claim is that even this problem is NP. And the idea to do so is by using something known as the systematic form of paradigmatic matrices.
Sorry, what's the problem? So you have
So I'm just converting this problem, rewriting it as this equality.
but you only have AG, right?
Yes.
And
And now what we claim is, like, what is the promise is, suppose this was the all zero vector. Like only bit flips are acting, no phase
so
shift.
you want to understand the minimum weight of an X that's in
Yes.
the kernel,
Yes.
whatever.
And
Yeah, that seems a lot like a classical coding question. The
It-
MDP.
yes, but now you have to construct you can say a
parametric
graph.
matrix which corresponds to the adjacency matrix of a graph.
Yes. Yes.
For the hard instances here, what does G look like?
So G is essentially you have to combine your paradigmatic matrix along with the generator matrix. So you can stack them one over other.
So, but graph theoretically, are they nice objects or like expanders? Or,
No. No. So you the property or the property of the paradigmatic matrices that I will be using is the fact that up to elementary row operations and column swaps, you can write your paradigmatic matrix in this format, which is known as the systematic form. And the nice thing about the systematic form is the generator matrix over here can be written as B transpose Y. And now if you stack H and G one over the other, that gives you a symmetric matrix. So you can interpret that as a graph. And now for that, if you want to, which slide should I raise?
Maybe just go down. Go to the
Press
next
the
one.
button.
It is.
No, but back to Manav's question, so it's true that I don't know how to lift the class, I don't know how to interpret a classical code as a quantum code,
Mhm.
but you can, from a quantum code, stabilizer codes are sort of a generalization of the notion of linear
Yes.
codes, but in this world, which can handle both bit flips and phase flips.
Yes.
So, in some sense, why doesn't the original proof of MDP just transfer over? That is, these are slightly more general object. And is it because distance is is a slightly different measure if you had worked with the same notion of distance?
It's somewhat related to that. So what you can do is you can set okay, so with this.
And maybe a question related to that. Why did the symplectic thing show up in the first place?
The symplectic inner product?
Yeah, in when we wrote it from the generator to the matrix form, and then
Yeah,
Because
because
that transformation interpretation of stuff on in the operator language in terms of F2 embedding.
The operator
So
language is
it shows up in the proof.
generators are elements from this 4 power n space.
Hmm.
It's nice to look at 4 power n as 2 power n and the nice subspace of f2 to the power.
I mean, the normal inner product would have shown up, right? Is it that the proof itself?
No, the normal inner product does not work nicely with this. This isomorphism, the normal inner product doesn't work nicely.
yeah, coming back to your question, it's mostly because of, as you said, because of the definition of the weight of a vector that you're defining. That is the main reason for it. Yeah.
Not weight, the definition of The distance of
symplectic weight.
symplectic weight.
Yeah. Yes, so now we have a matrix of this format. And this is nothing but saying that your, like, this can be equivalently written as your hx. So this is your h, and this is your g. So hx equals to 0 and gx equals to 0, which is another way of saying that x lies in your code as well as its tool. It lies in the intersection of this. But the problem over here is like, okay, we have this thing, but the issue is you do not have a handle over this mathematical object that you have. This can be very well be the all zero vector. The intersection of the code and its dual can be the all zero vector. But if somehow you are able to ensure that this code is self-orthogonal, like it is contained in its dual, then this intersection will always be equal with, right? And the way to do so.
And that was your more basic the notion of weight, because you're working with rate 0 codes. So usually, distance for a quantum code is defined as take the stabilizer.
Yes,
This
and
one, take its normalizer and take the minimum weight in the normalizer minus the stabilizer. That's going to give you this
yes,
one. Now, when it's rate 0, the stabilizer is the it's the ceiling.
Yeah.
Therefore, normalizer minus stabilizer, there's nothing in it.
Yeah.
So this is not the same notion as
No, in that case, the distance will be which is the least. So, what is the least weight element in your stabilizer? And below, if you look anything below that, you can detect it. So,
But distance of a code is not the thing in the stabilizer. It's in the normalizer minus the stabilizer.
if your normalizer is not empty.
Okay.
If
Normalizer contains more things.
if it is properly if it properly contains a stabilizer.
Okay.
But if it is only containing a single logical, like if you are encoding a single logical qubit, then in that case the notion of distance is there. Like it is defined as the minimum weight of the element in the stabilizer. Because anything below it you can detect.
Okay.
Like we can take it off.
Okay.
Sorry, just a nice question. Like in both these cases, we are defining. So I don't remember the whole formalism or CSS or stabilizer code, but you define distance in a way, but you are defining it in this way because you want to use it as a proxy for how much error correction can.
Exactly.
And here the right proxy is to take this different distance. No?
Yes. Yes. So, in order to ensure that you have this self-orthogonality condition, what we can do is you take a code over it and you map it by creating another copy of that code over it and just concatenating them with one another. And what one can notice is under this map pi, it is contained in its Euclidean group. Because we are working over f. And like this operation will just double the weight and it will so your whatever input instance of the code that you had, its weight gets doubled. So this is a reduction from MDP to this promise version. So your claim 1 prime, which was asking that whether this promise version is empty or not, is true. For now,
So like option was that you took an arbitrary code and you applied this operator on it.
And
That
then
makes the code self-orthogonal.
self-orthogonal, and then you repeat that entire stacking your parity matrix and your generator. Now, now, question is, can we use the same graph to prove claim one, which was that computing the distance of a graph stays in the Hardness order? So, in the general case, proof of claim one, we have the identity, and let's say we are using the same graph, and we have this left broken, and we want to solve the system. So I can verify this I as I n minus a and r cube. So now, and so let's see, yeah. So now the problem over here is, if you look at the upper half, this is just the identity along with the H matrix. And this is the identity over here, it's the identity along with the G matrix. So the structure of your parity check matrix and your generator matrix is lost in this kind of reduction. Because you're having an extra copy of identity in both the numerator in this upper part and the lower part. So now, is there can anyone see a way as to how we can fix it? Like how to go from this graph to another graph such that structure is preserved?
So I didn't get the issue.
So the issue is, like, if you look at the top half, you have this is your parity check matrix H, and you have an identity matrix attached to it. Right. So the structure of the parity check matrix is somewhat lost. The same goes for your lower half. You have this is the generator matrix G, and you have an identity attached to it. Right. So now it's no longer in the form of H and G. It's now in the form of IH and GI, if you want. So, like, is there any way by which we can fix it? I mean, we still want this to be a graph, but we still want to have that H stacked over G structure. Yeah. So, like, one way can be simply remove these extra copies, like replace them with zeros. If you do so, the graph over here, like the matrix over here, continues to be symmetric, and so it is still a graph. And now you have a matrix which is in the form of H, though separated by zeros. Similarly, even below it is in the form of G, but again it's up to a permutation of the variables. And now this entire problem gets converted to I n minus k p z equals to v1 to z n minus k x n minus k plus 1 to xn plus 0, and I p transpose z n minus k plus 1 to z n x1 to x x k. So this was x and minus k. And this is nothing but like find this solving this is essentially finding the minimum of your code and it's doing find the minimum of the distance of the code and its Euclidean rule. Because like if you set these two the variables, the set of variables involved over here and over here are disjoint. So you can set one of them to be all zeros and find a non-trivial solution over here and do the vice versa to the converse and take the minimum of those two. And that will be your minimum of this. So like, and I would say that this is the proof, but I have cheated over a bit, and the reason is I assume that this is NP hard. Yeah, but I think in the interest of time, I mean, there's proof as to why this is NP hard, but
What is NP hard?
this the problem corresponding to this. So if I consider the decision problem,
And the MDP was to compute distance of the code. But we are assuming that min of distance of C and distance of goal is hard to compute.
yeah, so min of this is at most t or greater than t. Yeah. And
If the NP hardness of MDP was for self-dual codes, then it's okay.
yes, but that is not.
That's
Yeah. In fact, that was the main reason for Kapshikar and Kundu using a different method altogether.
nice. And that's not known. In the sense that it's not known. It's not known false either.
Yeah, it's not known. Yeah. Not only for self-dual, even for self-orthogonal codes, it's not. Yeah. And yeah, so now, yeah, so about about the rate half code result, one can see that the very same matrix that we used for the minimum graph state distance, which was I 0, 0, I P transpose. If rather than computing the minimum graph state distance, we could if we can treat this as a parity check matrix corresponding to a code and try to compute the minimum distance of the code that is defined by this. That will also turn out to be this value, minimum of distance of C and distance of C to A. And the rate of that code is going to be half because this is an n cross 2 matrix. So that gives the hardness of rate half codes.
Sorry, so here you said we haven't seen that, we don't know that this problem is min dist.
We haven't I can explain it, but offline in interest of time. Yeah. So I think that would be only.
Yes, can you agree on the last statement? So you're given a code with a parity check matrix.
Mhm.
This statement you're claiming that you're gonna put a parity check matrix and to check if the minimum of that code, distance of that code or the dual code is less than or equal to or greater than t is an NP hard problem.
Yes.
And this you get it by reduction to the classical MDP.
Yes. So
Yeah.
so this problem acts as a bridge between MDP and the minimum graph distance problem. Or even the MDP and this problem of rate half codes.
This seems like a very natural question on its own. Because the
Yeah.
min
And like in literature, I don't think this was known before.
Just kind of.
Are there codes C where computing the mean distance is hard, but computing the mean distance of the dual is not? I mean, I don't know how to think of these quantities, like where they.
Say, okay, so consider this very code pi of C that we were having. The dual of this will be having distance 2. Like pi of C was essentially the set of vectors C comma C, where C lies in this.
You can come up with parity checks with the.
Imagine a code where you take a code and to that you add a very short vector.
Or you can
You
also
also add
add
a new code.
or you can also add zeros for that matter. Like if you add zeros to that code,
Adding
the
zeros to that code.
pad zeros to
Oh, add zeros to the code.
No, you just specify the code by its parity check matrix, which is composed of just low weight matrix. So the dual code you know has distance at most 5. Now you have to just go over 1, 2, 3, 4, 5. You check all of them. The other code is the one. So you can construct such codes. Yeah.
More questions? Let's time for answer.